So this video is going to be like slightly more theoretical than normal. There's not going to be much maths involved in this next couple of minutes. But we're actually going to get onto the different kinds of waves there happen to be, as we've discussed in the very first video in the series, is that there are technically four different kinds, and it depends on a couple of things. So it depends on how they vibrate relative to their direction of motion, and then another depending on how fast the wave is. So with their motion, they can either be longitudinal or transverse, and with their speeds, they can be either mechanical or electromagnetic. Now, before we go on, I would like to say that motion, you might see it as another word, and that word might be. Why has it done that? Whoops. I don't know why PowerPoint's done that. Let's try that again. The word is propagation. And that is just essentially the movement of waves, is when waves propagate. So we're going to get into longitudinal waves first. And it's waves that have the vibrations parallel to the direction of the wave. So what on earth does that mean? Now this diagram doesn't necessarily help, in fairness. But in case any of you are doing geography, which I have a separate channel on, there's latitude and longitude with the equator and the prime meridian. So, what the hell is a longitudinal wave by this definition? Well, if you'd imagine a person, so it's my beautiful rendition of a person, with a slinky on a wall, and they decide to push the slinky back and forth. So, I will draw the direction at which the person is pushing or pulling, so the force applied. So the force applied is actually going this way, so they're pushing it towards the wall and then sort of yanking it back, sort of like how you'd move a gear stick in a car. So the force is going that way. And in fact, the force is going that way, and the velocity is also going this way as well. So we'll see that this is different. Both the force and velocity vectors are parallel. And in fact, what you get from like a top-down view, so this is like from the side, but from the top, you'll see a bunched up thing, then you won't, then a bunched up thing, then you won't, and then a bunched up thing, and you won't, sort of like that. And then as the wave moves, these bunched up things will start moving back and forth in a sort of oscillatory motion. And these are actually given names, as we can see in that second paragraph. The compressions are these bits here, so when the wave is sort of bunched up, that's a compression. And then this one is not a refraction, it is actually rarefaction. So that often confuses a couple students, but this bit where the wave is slightly more spread out is known as a rarefaction. Okay, so hopefully that's clear enough. Next up are transverse waves, and I seem to have forgotten to rub off the annotations in this one, which is a bit silly of me. Whoops. But as you can see here, I've tried to draw on the force vectors. So the force vectors are in blue here. So we've actually provided a force going up and down, as opposed to in the direction of motion. So we can see that a transverse wave occurs when the vibrations occur perpendicularly to the direction of motion, as we can see here, as I said before. And each of these will always be perpendicular to the velocity vector at that point. Now, transverse waves are actually slightly easier to model mathematically, because we can actually use our normal sine function. So our good friends at sine and cos are still applicable for transverse waves. And in fact, transverse waves are slightly more common in real life than longitudinal waves. For example, the tides are actually controlled by transverse waves. So we're now going to get on to the speeds, or the ways you can distinguish speeds of waves. And the first one is mechanical. So mechanical, we say that it requires a media to pass through, so it cannot travel through a vacuum. The common example you might hear is that in space no one can hear you scream. The reason for that is because sound actually requires vibrations of molecules. So what I mean by that is, I'll do it up in the corner again, is that we have a loudspeaker here. There's a loudspeaker. And then the waves which come out of it sort of look a bit like this. So these are the crests of the wave. And in order for this to actually produce sound, little molecules that happen sort of anywhere, they start to vibrate. So they vibrate back and forth, or they might vibrate in sort of whatever direction they want. That's just the physics of entropy right there. However, in space, there aren't actually any particles per se. I'm doing air quotes, obviously you can't see it. But there aren't any particles in order for the sound to vibrate off of. So yeah, in fact, sound is mechanical, as we can see about this example. And the other kind is known as electromagnetic. So we're actually going to get onto the electromagnetic spectrum in about a chapter or so. But electromagnetic waves are actually different forms of light, and they travel at light speed. So they don't actually require a medium to pass through. That's just because it's light. And another thing as well is that these can also be called electromagnetic radiation. And this also motivates why we can see things, so see spatial events, but we can't actually hear them unless they're within our atmosphere. Because when the sound of objects is not within the bounds of our atmosphere, then we can't hear it. Because again, the sound and the movement doesn't cause any vibrations within the internal molecules. So just to summarize, we can define waves as mechanically transverse, which is like the vertical motion on a string, mechanically longitudinal, which is sound, but we also have electromagnetic transverse, which is most of light. And a lot of teachers don't seem to care about electromagnetic longitudinal, but that actually does exist in the form of plasma vibrations. So plasma is like the fourth state of matter, with your solid, liquid, gas, and then plasma. So the vibrations in plasma actually exhibit electromagnetic longitudinal motion.